All right, mathematicians, let's get started with areas of polygons and composite figures, section 11.3. Our objectives are to find areas of rhombuses and kites, find angle measures and areas of regular polygons, find areas of composite figures, and our essential question, how can you find the area of a regular polygon? Our first area formula is for a rhombus or kite. It's the same formula. Essentially, you'll multiply your diagonals and divide by 2. So half of diagonal 1 times diagonal 2. Alright, so let's practice the formula for each of these examples. Our first example, we have a rhombus. We know it's a rhombus because all 4 sides are marked congruent. So write your formula first step, always, always. Second step, substitution. So we substitute 6 and 8. Multiply all those numbers together, area is 24 square meters. For kite, first step, write your formula. It's the same formula. Half of your diagonal 1 times diagonal 2. We've got diagonal 10 and a diagonal of 7. Multiply all that together, 35 square centimeters. All right, let's talk about finding angle measures and areas of regular polygons. Just to review, regular means equilateral and equiangular polygon. And polygon can be any number of sides. So here are the parts of a regular polygon inscribed in a circle. We've got our center, and in this picture it's called center P. It's the center of the circumscribed circle, also the center of the polygon. We've got our radius, super important, it's the distance from the center to the vertex of a regular polygon. In this picture, our 2 examples are segment PN and segment PM in red. Apothegm is a new vocabulary word. It's the perpendicular distance. I added in the symbol for perpendicular here. So the perpendicular distance from the center to any side of a regular polygon. In this case, it's segment PQ, blue. And then you have your central angle, which is an angle formed by 2 radii drawn to the vertices of the polygon. In this example, it's angle MPN. You just need to recognize that you can have 6 different radii. You can also have 6 different apothegms. And you can have 6 central angles because there are 6 sides. So if you increase to 7 sides, you'd have 7 of each of those items. Alright, so let's practice finding angle measures in a regular polygon. So we have regular pentagon inscribed in circle F. So find each of the following measures. All right, measure of angle AFB. Just to start off, we've got a central angle. Since we have a central angle, that means we need to take 360 degrees and divide by the number of sides, which is 5. So each central angle on this pentagon is going to be 72 degrees. So the measure of angle AFB is 72 degrees. Next, we want the measure of angle AFG. All right, we see that segment FG is the apothegm, therefore the altitude, of isosceles triangle AFB. So that makes FG bisect angle AFB. So if we take the measure of angle AFG, it's going to equal half of AFB, therefore 36 degrees. So if we take this little small angle right here, it's going to be 36 degrees. All right, next we want to figure out the measure of angle GAF. Well, we notice that the sum of interior angles of any triangle is 180 degrees, and we have a right triangle because the altitude, the apothegm is the altitude, therefore a right triangle. So we know the 90, we know the 36, we subtract both of those from 180, so measure of angle GAF is 54 degrees. All right, next we have finding the areas of regular polygons. So it requires a special formula, and this formula is available on your formula chart. So the area of a regular polygon is always half the apothegm, so that lowercase a, as identified in your definition, times the perimeter of the regular polygon, which is your capital P, also in your definition. And a variation of the same formula is to take that capital P, which is the n times s. N stands for the number of sides on the polygon, and S stands for the length of the side. So to get the perimeter of your polygon, take the number of sides times each side length. Alright, so let's practice our regular polygon formula. We've got a nonagon inscribed in a circle with a radius of 4 units. Find the area of the nonagon. Alright, for this one we want to start by identifying the central angle, JLK, to be 360 divided by 9. So that makes the entire angle 40 degrees. The central angle is 40 degrees. And then we know that the apothem LM bisects the central angle in half, making this smaller angle 20 degrees. And I need the length of my apothem, which is LM, and I need the length of my side. So I can use this small right triangle to help me get that, and I'll have to use my trig ratios. So to find the side lengths of the legs, we need to use our trig ratios. So use your formula chart if you don't remember them. Alright, so we can set up our sine ratio to help us figure out the length of MK, which is going to be opposite over hypotenuse. So MK divided by LK, substitute your 4, that's what we know. We know our hypotenuse to be 4, so then we multiply that on both sides, so MK is 4 times sine of 20 degrees. Then to find LM, we would do cosine. And cosine is going to be adjacent divided by hypotenuse. So we have our SOHCAHTOA to help us remember the order of our ratios, and we also have our formula chart. So we substitute in, LM comes out to be a length of 4 times cosine 20 degrees. Alright, so we know our lengths. So our side is going to be double the length of MK. So we double this, resulting in 8 times sine 20 degrees. And then our apothem is 4 times the cosine of 20. So substitute both of these into our formula. Type all that into your calculator. 9 is the number of sides. And then your perimeter, one side, is 8 times sine 20 degrees. Type it in, you get 46.3 units squared. Alright, so let's use our new formula, regular polygon formula, to find the area of this tabletop, which has a whole bunch of ceramic tiles. So we know that the regular octagon has lengths of 15 inches for each side, and we see that here on our label. And then we have a radius, which is R to Q, 19.6 inches. So what is the area that is being covered? So first step is we want to find the perimeter of the tabletop. So to find the perimeter is we take all 8 sides and multiply it by each side length, which is 15, and get 120 inches. Our next step is to find the apothem. We know the apothem is segment RS of triangle PQR. So let's get a sketch of our individual triangle, and we can draw radii RP. So we've got radii RP, and then the RQ that's already identified in the original picture, RQ, and labeled 19.6. Then you can sketch in your apothem, which is always the altitude perpendicular to the side of the polygon. We know the full length is 15, so half of that would get us the 7.5. So now we've got a right triangle that we can identify using, we can use Pythagorean theorem to get this apothem length. So again, to get length of QS, take half of the full length, and then use Pythagorean theorem to get your apothem. And then your final step is to plug all these numbers that you've figured out in steps 1 and 2 into our new formula. Half of the apothem, which always use exact in your formula. And then our perimeter was 120, and type all that in the calculator and then round at the very, very, very end. So the area you're covering with tiles is about 1,086.5 square inches. Alright, now let's look at composite figures. Basically, when you're finding the area of composite figures, composite just means more than one figure put together to make one giant figure. So in order to find the area of composites, you always want to identify what shapes make up your composite. In this particular example A, our composite figure consists of a regular hexagon and a trapezoid. So the next thing you want to think about is, in order to get the area of this composite, what other areas, individual area regions, do I need to figure out? So I will need to figure out the area of the hexagon, and I'll call that area 1. And I need to figure out the area of the trapezoid. I'll call that area 2. So we've talked already about regular hexagon. So go ahead and write out your formula. Alright, so it's 1/2 this apothem times the perimeter. So I don't have my apothem identified, and I only know half of my side length. So I can figure out the rest of my side length by doubling that 0.8. So let's do that. So I get a side length of 1.6 when I double the 0.8. Now I can find perimeter. There's 6 sides, so 6 times the 1.6. So my capital P perimeter value is 9.6 inches. Now for me to find the apothem, I know I have a right triangle with at least 2 side lengths known. It looks like the hypotenuse and a leg. So I can plug that into my Pythagorean theorem. So I take the hypotenuse squared minus the leg squared and then square root the whole thing. So my apothem is square root of 1.92 to be exact, and type that in the calculator, get approximate. So now I can plug in all those numbers into my formula for regular polygon and get approximately 6.651. Alright, next I want to work on my trapezoid, so you got to look that formula up if you don't remember it. So it's half the height times base 1 plus base 2. Substitute your values, so we know the 1.5 is the height, and 1 and 2 are the base. And then just work towards simplifying and solving, coming out to 2.25. So now to get the composite, we just add both of those areas together, resulting in about 8.901 square inches. Alright, for example B, again, first step, figure out what your figures are that make up the composite. This one has a composite of a sector, so just part of a circle, and a triangle. So to get the area of all of the composite, we need to add the first region, which we'll label A1, the sector, and then the area of the triangle, our second region. So you figure out your sector region, that's based on lesson 11.2. So set up your equation, substitute your values, area of region 1 comes out to be 49/6 times pi, that's the exact answer. And then area of a triangle is half the base times the height, our base is 7. And then our height is 4. That comes out to be a product of 28, so half of 28 is 14. Then you want to add those two regions together. Type that in your calculator, and the grand total for the composite area is about 39.656 square centimeters. Alright, for this final example, part C, I want you to try this one on your own. So pause the video here, think through all your steps that I provided an example for in A and B, and see if you can do this entirely by yourself. Alright, let's check our answers. So know it's a composite of a kite and a parallelogram. So we know we're finding the area of the kite, first region, and area of the parallelogram, second region. So the kite comes out to have an area of 21. Area of parallelogram comes out to be 12. And then together, the two regions combine to be a composite area of 33 square feet. And that's all for today's lesson. Bring your notes and clarifying questions to class. See you then.